claimed the James Webb Space Telescope spotted a large object about 10 light years away moving toward Earth. The Post's claim that the telescope captured the object changing its trajectory.
December 19th is not just another date on the astronomical calendar. For telescope operators around the world, IT is a moment of quiet tension, the kind that only happens when something rare drifts into view. 3I Atlas is not a planet, not a comet in the usual sense, and not something that belongs here. It is an interstellar visitor, only the third of its kind ever identified, and the first discovered by the Atlas survey with enough lead time to prepare a coordinated global observation campaign. On December 19th, telescopes are not looking for spectacle. They are looking for clues. Tiny ones, subtle ones, the kind that rewrite textbooks years later. At first glance, 3I Atlas does not look impressive. Even through powerful instruments, IT appears as a faint point of light, barely distinguishable from background stars. There is no dramatic tail stretching across the sky, no obvious glow that screams comet. And that is exactly why astronomers are excited. Interstellar objects do not behave like the comets and asteroids born in our solar system. Their chemistry, surface structure, and motion carry information from entirely different stellar environments. December 19th is when Earth's position, the object's trajectory, and observational geometry line up well enough to allow the cleanest measurements yet. One of the first things telescopes expect to confirm is how active 3I Atlas really is. Earlier observations suggested only weak outgassing, if any at all. That already sets it apart from Oumuamua, which showed non-gravitational acceleration without a visible coma, confusing astronomers for years. If 3I Atlas begins releasing gas or dust as it warms slightly, even at a low level, sensitive instruments like the Very Large Telescope and the Gemini Observatory can detect it. They are not just looking for a tail. They are looking for spectral fingerprints of molecules like carbon monoxide, carbon dioxide, or water vapor. Even a trace detection would be enormous, because it would reveal the volatile content of a body formed around another star. Spectroscopy is the real prize on December 19th. While images tell us where the object is and how bright it appears, spectra tell us what it is made of. Telescopes equipped with high-resolution spectrographs will spread the faint light of 3I Atlas into its component wavelengths. Astronomers expect to see whether its surface reflects light more like a rocky asteroid or an icy comet, or something in between. The slope of its spectrum, especially in the visible and near-infrared range, can indicate whether its surface has been reddened by long exposure to cosmic radiation in interstellar space. A very red spectrum would suggest millions or even billions of years drifting between stars before it ever encountered our sun. Another major focus is rotation. Objects like this tumble, spin, or wobble in ways that reveal their internal structure. On December 19th, telescopes will monitor tiny changes in brightness over time, building what astronomers call a light curve. If the brightness fluctuates regularly, IT suggests a stable rotation period. If it fluctuates erratically, IT may be tumbling chaotically. That distinction matters. A stable rotation could imply a relatively solid body, while chaotic tumbling might indicate a fractured or elongated shape. With Oumuamua, extreme elongation became one of the most controversial findings. Astronomers want to know if 3I Atlas is similarly unusual or if Oumuamua was an outlier. Radio telescopes will also be listening, not because anyone expects artificial signals, but because radio observations can reveal gas emissions invisible at optical wavelengths. Facilities like ALMA can detect faint emissions from molecules that are otherwise impossible to study. Even a non-detection is valuable. If 3I Atlas shows no radio emissions at all, IT would suggest a dry, devolatilized object, possibly more asteroid-like than comet-like. That would raise new questions about how common rocky debris is in other planetary systems and how it survives ejection into interstellar space. Astrometry is another quiet but critical goal. On December 19th, telescopes will measure the object's position with extreme precision. This allows astronomers to refine its trajectory backward and forward in time by tracing its path through the galaxy. They can estimate where it came from and how fast it was moving before it encountered the sun. If its velocity matches that of nearby stellar populations, IT might hint at a rough region of origin, even if the exact star system remains unknown. These calculations also test our models of how planetary systems eject material during their formation. Thermal measurements are also expected to play a role. Infrared telescopes will attempt to measure how much heat 3I Atlas absorbs and R emits. This provides insight into its size and surface properties. A dark, porous surface behaves very differently from a shiny, rocky one. If the object is darker than expected, IT could explain why it remained undetected until relatively late, even if it is larger than initially estimated. Size matters, because it affects how common such objects must be. A large interstellar object passing through our solar system implies that countless others exist unseen. There is also interest in whether 3I Atlas shows any non-gravitational acceleration. Even tiny deviations from a purely gravitational path can be detected with careful tracking. If such acceleration is present, telescopes will look for physical explanations, such as asymmetric outgassing or radiation pressure acting on an unusually thin structure. After the debates surrounding Oumuamua, astronomers are cautious. They are prepared to test every mundane explanation first. December 19th offers the best chance to catch subtle effects before the object fades further. What telescopes do not expect to see is just as important. They do not expect bright jets, dramatic fragmentation, or rapid changes in brightness. If those did appear, IT would be a shock. The current expectation is that 3I Atlas is relatively inert, a quiet traveler revealing its secrets slowly. This restraint is actually reassuring. It allows scientists to study it as a relatively unaltered sample of material from another star system, rather than something actively reshaped by solar heating. Coordination matters on this date. Observatories in different time zones will hand off observations, creating nearly continuous coverage. Space-based telescopes will complement ground-based ones by avoiding atmospheric interference. Each instrument adds a piece to the puzzle. Optical telescopes measure shape and brightness. Infrared telescopes probe temperature and size. Spectrographs analyze composition. Radio arrays search for faint molecular signatures. No single observation is decisive on its own, but together they form a coherent picture. There is also a sense of urgency. Interstellar objects move fast. 3I Atlas will not linger. As it recedes from the sun, IT will grow fainter and harder to study. December 19th represents a sweet spot, when it is still close enough for detailed measurements, but far enough from the sun's glare to observe safely. Miss this window, and many questions will remain unanswered for decades, until the next interstellar visitor appears. Beyond the technical goals, there is something quietly profound about this moment. Telescopes on Earth, built by a single species on a single planet, are examining a fragment of another solar system. This object formed around a star that may no longer even exist in its original form. Its atoms were assembled in a protoplanetary disk far from here, long before Earth formed. December 19th is not just about data points and spectra. It is about context. About understanding that our solar system is not unique, and that pieces of other worlds pass through our cosmic neighborhood more often than we once believed. By the end of the day, astronomers do not expect headlines announcing a solved mystery. What they expect is something more valuable: constraints, better limits on composition, shape, activity, and origin. Each constraint narrows the range of possibilities. Each one feeds into models of planet formation and stellar evolution. When future interstellar objects are discovered, scientists will compare them to 3I Atlas, asking whether it represents a common class or a rare exception.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.